In these next few chapters, we're going to look at characterization methods, basically analytical chemistry methods to take a sample of chemicals and determine what's in them. In this chapter, we're going to look at IR spectroscopy and mass spectrometry. Spectroscopy involves shining light on a sample and seeing how the light interacts with that sample. All right, so usually you have a detector that looks for changes in the light that you're shining on your material. All right, now when I say light, I'm not talking about just solely visible light, though we will eventually look at UV-vis spectroscopy that does use visible light, along with obviously UV light. But I'm talking about electromagnetic radiation in general. All right, so we're talking about the whole spectrum of electromagnetic radiation. I'll refer to that as light, okay, not just visible light. So when we look at light, remember you have light that travels either as particles, photons, or we could describe it as traveling in waves, right? And these are all legitimate ways to think of electromagnetic radiation, all right? Whether as basically they have an energy, they have a wavelength, they have a frequency. These are different sort of characteristics of light that you want to look at when you are describing the different parts of that electromagnetic radiation spectrum. Okay, so just this hopefully should be a little bit of a refresher from physics if you've already taken a physics course, or if you haven't, hopefully this, I'll try and stick to the basics, and if you do eventually go on to take a physics course, you will, hopefully recognize this. But basically, when you look at light being described as a wave, you could describe the length of the wave. So basically, you could, there we go. So if you have imagine you have an x and y axis here, and you think of a wave as looking something like this. This actually would go on and continue repeating, of course. If I take a point, like let's say from one crest to another crest, that distance is a wavelength. All right. Now you could measure it at different points. So a lot of people might take this point and see that point come back again over here. That's the same distance, but that is a wavelength, which you'll see sometimes represented with the Greek letter lambda. Okay. The frequency is the number of waves that fit into a given unit of time, and we represent that with the Greek letter nu. Okay, it looks a little bit like a V. I think if you're drawing the Greek letter nu by hand, it tends to look like this. And in the case of both wavelength and frequency, we can tie those to the energy of the radiation using these corresponding formulas. So frequency is directly proportional to energy. They are linked together by Planck's constant, represented with the letter h. And energy is also equal to h times c, which is the speed of light, divided by lambda, which is the wavelength. So in other words, wavelength is inversely proportional to energy. Okay, just as it's your frequency is also equal to c over lambda. Okay, so in other words, your wavelength is also inversely proportional to your frequency. So in other words, the shorter the wavelength, the higher the energy, the higher the frequency of the light. Okay, so here is our electromagnetic spectrum. We have our lower energy or longer wavelengths going all the way down to radio waves, including microwaves. All right, so microwaves are actually a little bit on the shorter wavelengths of radio waves. Then we have infrared radiation. All right, and we have visible light over here, which of course has all the colors of the rainbow. So infrared, the word infra means less than or lower than. So infrared light is lower energy than the red part of our visible spectrum. Okay, now of course we go through the colors of the rainbow, and at the higher energy or shorter wavelength end, we have the violet end. So when we get past that, we have ultraviolet. Okay, so ultraviolet means more than violet or higher energy than violet. And if we go past that, then we get to X-rays and gamma rays. And of course, those are the higher energy forms of the electromagnetic spectrum. So gamma rays are the highest energy types of light out there. They have very short wavelengths, very high frequencies, high energy. So basically, when it comes to spectroscopy, we're going to take different parts of this spectrum and shine that kind of light on our sample and see what happens. All right, so in the next chapter, we're going to look at NMR spectroscopy. So there we will take radio waves and fire radio wave pulses at our sample and see the effect on that. There's also a magnetic field involved with that, hence the M in nuclear magnetic resonance. In this chapter, we're going to look at IR spectroscopy, and so here we're going to use the infrared part of that spectrum. Okay, in 2 chapters, we'll look at UV vis spectroscopy, as I mentioned earlier, and of course the UV, of course, there stands for ultraviolet, and the vis part of that is visible spectrum. Now, each of these tell us different things. Okay, and we'll go into more detail on NMR in the next chapter, but basically NMR spectroscopy will tell us kind of the environments the different atoms are in, and that tells us a little bit of how they're connected to each other. All right, you'll see that NMR is arguably the most useful analytical technique for organic chemists. Once we get past the next chapter, we're going to be using NMR spectroscopy quite a bit. IR spectroscopy is very useful for identifying functional groups. You've already seen some IR just through lab last semester, and you've probably noticed that we can quickly identify the presence of something like an alcohol group or carboxylic acid just by seeing the relevant peak in our IR spectrum. Okay, and we'll go into more detail into how to read an IR graph or spectrum in this chapter. All right. UV vis spectroscopy, we'll get into more detail on that in a couple of chapters, but in a nutshell, we're going to look at conjugated pi systems using those. So in other words, systems that involve alternating double and single bonds. Earlier I mentioned that spectroscopy involves the interaction between matter and light. You shine light on your material, and you have a detector picking up how that light is changed. Now, this interaction happens because matter behaves, it exhibits quantum behavior once you get down to the molecular level. So when you shine light of a particular energy that corresponds to or is in resonance with a particular state of the matter, so a particular vibrational or rotational state, that's what the detector is picking up. Right, you find like that wavelength of light, that energy of light missing usually. All right, so in the case of IR spectroscopy, this typically has to do with actual vibration of bonds, and we'll go into more detail on that. And we'll see that there are other forms of these quantum states that we vary depending on the light that we're using and the type of spectroscopy we're using. Okay, so we'll go into more detail with this in the other, basically in the different kinds of spectroscopy we'll look at in these next few chapters. All right, so so basically IR light happens to be in the particular energy range that corresponds to these vibration of bonds. So your bonds absorb these photons of light or these wavelengths of light, and if it corresponds to the energy of that vibration, your detector notices that difference in light, that wavelength of light is being absorbed. Okay, so what kind of quantum states are we talking about when we talk about these vibrations? You can look at the sort of back and forth vibration or stretching vibration between 2 atoms connected by a covalent bond. You could look at the interaction between 2 atoms as they sort of bend towards each other. Okay, so kind of like this interaction here, what we call scissoring. You can imagine that these 2 bonds are sort of moving closer and further apart. Okay, then we could also have a twisting motion, right? So if you have some sort of central axis and these 2 atoms move clockwise or counterclockwise around it. Okay, all of these are associated with some energy, and the energy will correspond to a wavelength of light that's in that infrared range of your electromagnetic spectrum. Infrared imaging or thermal imaging works on the same principle, actually. So if you're familiar with night vision goggles, they work through not visible light, but infrared radiation coming off something. So even if you don't have a lot of visible light present, night vision goggles can detect heat, essentially, rising off images, and you kind of get an image of things that are present that way. So infrared spectroscopy works on a similar principle in that it's looking for this light, or at least the detector picks up light that's making its way through the sample. All right. Now, the only difference there is, of course, you're shining the infrared light on your sample, and your detector's picking up what's making its way through the sample. Now, why do we have different wavelengths of infrared light that get picked up? The reason for this is that the energy gaps between these different vibrational states, or these different quantum states, is different. All right. So if you have a larger gap in between these states, that corresponds to a shorter wavelength of light that would get absorbed to cause that that difference in state, to cause that change in state. Yeah, so essentially all you're doing is you have in your infrared spectrometer, you have your sample that you usually have loaded either onto a salt plate or mixed in with a potassium bromide pellet, and you put it into a certain holder, and the device, the instrument shines infrared light through your sample, or either the plate or the pellet that you're using. And of course you have a detector on the other side that then sees what light makes its way through the sample to the detector. Okay, now the device, of course, then shines a different, a whole range of different frequencies of infrared light. And the detector notices how the intensity of the light changes as you change the frequency of light. All right. Oh, a quick note here about why we use a salt plate. All right. So either sodium chloride in the case of liquid samples. You might remember we used that back last semester when we did our lab with eugenol. I took your samples of eugenol, put a couple of drops on a flat salt plate, and that went into a little metal holder that I slid into our IR spectrometer. If we had a solid sample, we would use potassium bromide. Basically, you mix it in with the potassium bromide, you grind it together, and then you put it into a press, which you just compress into a little pellet. Okay, and that goes into a similar metal holder, right? The reason for this is that these ionic compounds don't interact with infrared light. They would interact with electromagnetic radiation, but just not in that infrared region. All right, so it's actually a good material to hold the substance that we are examining, because we know that the infrared light will only interact with the material that's embedded into our salt. Okay, so what does an infrared spectrum look like? You guys, again, would have seen one in lab last semester, but basically it looks like this, right? On our x-axis, we have what are called wave numbers, which are essentially kind of a derivative of frequency. All right, they're kind of like an inverse of your wavelength, basically. And on the y-axis, we have percent transmittance. In other words, how much infrared light of that particular wave number makes it to the detector. All right, so wherever you see these sort of peaks, with these sort of downward pointing peaks, you know that your sample has absorbed that infrared light. Okay, so what I mentioned that wavelength numbers are tied into to wavelength and frequency, this is the actual calculation. So to calculate a wave number, you take the frequency and you divide it by the speed of light. So if you're trying to figure out how the units work there, remember frequency is the number of waves per unit time. So usually it's given in inverse seconds or hertz, okay, which are the same thing. Speed of light is meters per second, right? And so, or at least some unit of distance per second. So if you take your per time and divide by, a distance per time, you get inverse distance. So in this case, using centimeters, that's the scale we're going to use, or inverse centimeters rather. Okay. Oh, this question is kind of important. So how are wave numbers in energy related? So basically, the shorter the wave number. So if we go back to this calculation, notice that frequency and wave number are directly proportional. Well, remember, frequency and energy are also directly proportional, right? So in other words, wave numbers increase as the energy increases. Okay, so as we go to the left of our diagram, the energy of light is increasing. All right, so as we have higher wave numbers here on the left, the energy of our light is also increasing. Okay, so how do we read an IR spectrum? When we look at this graph, we want to look at the different peaks that are present, and we want to examine them for three main characteristics. We look at the wave number, so where on this x-axis is our peak showing up. We look at the intensity, in other words, how deep are these peaks. All right, so notice that we have, for example, very strong peaks over here versus very weak peaks over here. And then, of course, we want to look at the shape of the peaks. Are they very sharp peaks, or are they kind of rounded like this, very broad peaks? So let's look at each of these in turn. For a wave number, we tie this into the bond strength and the mass of the atoms that we're looking at. Okay, that's kind of what determines the wave number for the peak that we're looking at. All right, so if you want to see the actual formula behind it that's described here, the bond strength is directly proportional to our wave number. So generally, the stronger the bond, the higher the wave number there. Okay, the reduced mass over here is on the denominator. So reduced mass is inversely proportional to our wave number. Now, what is the reduced mass? Well, if we're looking at a bond between two atoms, the reduced mass is the product of those two atoms' masses divided by the sum of their two masses. All right. So generally speaking, reduced mass is directly proportional to, well, the mass of your atoms. And we can see that that then in turn is inversely proportional to our wave numbers. So in other words, the heavier your atoms, the lower your wave number. Okay, so something to keep in mind there when, in a nutshell, you want to determine, or you're comparing different types of stretches and you're trying to figure out where will these wave numbers show up? Where will these peaks show up at with what wave numbers? Okay, so let's see some examples here, and you can kind of see this in practice. All right, so let's look at a few bonds between carbon and other atoms. So as we go through each of these examples, all right, so we've got carbon connected to a hydrogen, to a deuterium, which remember is just an isotope of hydrogen with an extra neutron, so it's a hydrogen 2. Oxygen and chlorine, you see that we are increasing the mass of our atoms connected to carbon. Okay, so this would increase our reduced mass. Well, remember, our reduced mass is inversely proportional to our wave number, right? It's on the denominator here. So as our mass increases, and therefore our reduced mass also increases, our wave number is going to decrease. And you can see that by the decreasing wave numbers for each of these bonds. Now, let's pick two atoms and change the strength of the bond between them. So if we go from a triple bond between carbon and nitrogen to a double bond to a single bond, remember the only difference between these, okay, all three of these bonds have a sigma bond between our carbon and nitrogen. The only difference is that we have extra pi bonds as we go to a double or triple bond. So our triple bond here is going to be the strongest, right? It's got a sigma bond and 2 pi bonds. And our single bond, which is only a sigma bond, is our weakest. Notice that the wave number is larger for our stronger bond, and it's lower for our weaker bond. Okay, so again, you can see how the our bond strength is directly proportional to our wave number. So, with that in mind, where do we see particular bonds? Okay, this is very important when you are looking at your spectrum and you see peaks in certain ranges, and you want to know what they correspond to. Okay, so the general rule of thumb is, as if you look towards the left of your spectrum, so from 2700 wave numbers upwards, you're generally looking at things bonded to hydrogen. Okay, now in the 21 to 2300 range, you're looking at triple bonds. In the 1600 to 1850 range, you're looking at double bonds. And then below that, you're looking at single bonds that are not connected to a hydrogen. Okay, so this range over here tends to be a bit of a mess. We'll talk about that in a second. But so you'll find that these types of peaks, these ranges here, are what really help us see various functional groups. So we call that region the diagnostic region. So that's really what's going to show us the type of functional groups we're looking for. The region over here with the single bonds is what we call the fingerprint region. So you have this sort of indistinct sort of mixture of all these bonds, and like I said, there's lots of them and usually a mess of them. But that being said, if you do have a sample to compare it to, it hopefully should line up, kind of like matching fingerprints, hence the name. All right. So let's have a look at our diagnostic and fingerprints for this for an example spectrum. So here we have 2-butanol, all right, and this is a spectrum for that molecule. And you can kind of see that that distinction between our fingerprint region, which, like I said, is a whole mess of peaks here. But if we look at the diagnostic region, again, there are a few clear peaks that give us an insight into what functional groups we have present. All right, so you can see here that we have, especially this nice broad peak here, is kind of characteristic of alcohol groups, and that kind of is very easy to pick up here in this diagnostic region. Okay, here is 2-propanol, all right, a very similar molecule, and again, you can see that functional group, that alcohol group, showing up pretty clearly in that diagnostic region over here. Okay, so if we were to compare the two, all right, notice that if we were trying to line up are these two spectra of the same molecule, you could look at that that fingerprint region and see that these do not all correspond to the same peaks, right? But more importantly, I think if we look at the diagnostic region, seeing that this broad peak over here, we know that we're dealing with alcohol groups. Okay, so when we look at the strength of of 2 bonds, right? Remember, that bond strength is directly proportional to our wave numbers, right? So let's say we compared a carbon-hydrogen stretch with an oxygen-hydrogen stretch. Okay, if we look at the wave numbers for those two, okay, we have lower wave numbers for the carbon-hydrogen stretch. Okay, so actually if we go back to this, you can see, looking at these bonds, I kind of already gave this away by mentioning that this broad peak over here is an alcohol group, and we'll see why later on. Why does it take that broad nature when we look at the shapes of peaks? But for now, just looking at the wave numbers, you could also figure out that that is our oxygen-hydrogen stretch, because we know that in this far downfield, right, at these higher wave numbers, these peaks have to come from bonds with hydrogen, right? That if we go back to our little sort of template here, we can see that that region is with bonds to hydrogen. So we know that these have to be either oxygen-hydrogen or carbon-hydrogen bonds, right? Well, if we look at bond strength, and we know that oxygen-hydrogen bonds are stronger than carbon-hydrogen bonds, that alone will tell you that this peak down here is from the oxygen-hydrogen. Okay, so that peak that's a little bit further down must come from that OH bond, okay, because those bonds are stronger and therefore have a higher wave number. Okay. So let's have a look at some other different stretches for our particular bond. So now let's compare three types of carbon-hydrogen single bonds. Notice that the hybridization of the carbon affects the wave number. So here we have an sp3 carbon, all right, and that CH bond shows up at a 2900 wave numbers, around that range. With an sp2 carbon, we see that that peak shifts further up. We have a higher wave number, and with an sp hybridized carbon, it's even higher, to about 3300. Okay, so since our wave numbers are dependent on the strength of bonds and the masses involved, well, we know this is not due to the reduced mass because we have the same atoms involved here, right? So it has to come from the bond strength. The hybridization of that carbon and the way that orbital overlaps with the hydrogen changes the strength of the bond. Okay, and it probably makes a little bit more sense when you think about the size of the orbitals involved, right? So if you have an sp hybrid orbital, those orbitals are smaller, right? Because they've got more s character, and therefore you're going to have more overlap with the s orbital of your hydrogen atom, and that is why then your wave number is going to be higher. Okay, so with that in mind, that itself will also give us a useful piece of information when we're looking at the wave numbers of certain bonds. We can use that 3000 number there as kind of a little, it's just sort of a divider or a border or benchmark, I guess. And we know that if we have an sp3 hybridized carbon, in other words, an alkane, that those peaks with those carbon-hydrogen bonds will show up at a wave number lower than 3000. But for alkenes and alkynes, okay, where we have a CH bond that's attached to an sp2 or sp hybridized carbon, those are going to show up above 3000. Okay, so that's something that helps distinguish those types of bonds. Okay, a quick note here about those, of course. Please note that this is not the carbon itself that does that, but a carbon attached to a hydrogen. So you do need a hydrogen attached to that carbon. So for example, if you have a terminal alkyne, yeah, you can figure that out. But if your alkyne's an internal alkyne, where there are no hydrogens attached to those carbons, you're not going to see this peak here. Okay, so watch out for that. Okay. So here are some examples of different, alkenes and alkynes. Let's see if we would have any peaks that would be above 3000 wave numbers. Okay, so feel free to pause this video while you think about this. Okay, so if you're back now, let's go through each of these examples in turn. So over here we have an alkene. Now again, remember, we need a hydrogen attached to one of these sp2 carbons, and what's not shown here is this carbon-hydrogen bond. So this would actually show up somewhere above 3000 wave numbers. Over here, now this alkene doesn't have any hydrogens attached to those sp2 carbons, so we won't see those CH bonds beyond 3000. The only other CH bonds here are belong to sp3 hybridized carbons, and they would show up below 3000 wave numbers. Okay, though of course, if you do want to look for a peak that is above 3000 wave numbers, you'll of course see this OH bond. Okay, that'll be a broad peak further downfield at those higher wave numbers, as we saw earlier. And then if we look at this example here, there will be no peaks beyond 3000. So notice here we have an sp hybridized carbon, an sp hybridized carbon, but since this alkyne is internal, there are no hydrogens attached to those sp carbons, and therefore those will not show up in that range for carbon-hydrogen bonds. Likewise, for this alkene over here, this is a tetrasubstituted alkene. There are only carbons attached to those sp3 sp2 hybridized carbons, and therefore you won't see a CH stretch from those sp2 hybridized carbons. So where are all the CH stretches? They're all on these methyl groups, right? So we have these, the CH3 over here, a CH3 over here, a CH3 over here, and here. And so all of those will show up below 3000 wave numbers. Okay, so we will not see anything above 3000 for that. All right, what else affects wave number? Well, resonance can affect your wave number because now you can have a bond that has partial single and double bond character. Carbonyls are great examples of this because we have a very common resonance structure for a carbonyl that has a single bond, right? So if these pi electrons go up to that electronegative oxygen, all right, notice that we now have that carbon-oxygen bond having some single bond character. Okay, so keep in mind that causes your bond to shift accordingly, right? Remember, your double bond is a stronger bond than a single bond, and therefore this would show up at a higher wave number, and this would be at a lower wave number. So the more stable this resonance structure is, the lower your wave number for that carbonyl. Okay, so if a carbonyl normally shows up at about 1720 wave numbers, and you get a peak that is at a number lower than that, well, that tells you that you have a resonance structure that stabilizes, that gets stabilized with this partial single bond character. Let me show you some examples so you can see what I'm talking about. So here we have a conjugated ketone, right? So here we have a double bond where we can have these electrons get pushed around not just between these two atoms, but all the way to these atoms. So if I were to draw an electron pushing diagram here, if I have these electrons move up here, all right, and I have some partial bond character here, a partial positive charge here, I could also have these electrons move over here, okay? And that would give us a resonance structure that looks like this. Okay, so we have our partial positive charge over here and our partial negative charge over here. All right. So again, my point here is that, and of course you have like the resonance structures in between this, but my point is that we've got multiple resonance structures that have the single bond character here. Okay, and this is obviously more stabilized then because you've got those charges spread out over more atoms. Okay, so instead of showing up at a wave number of 1720, it shows up at the lower 1680 because it has more single bond character. Okay. Over here we have an ester. All right, so we have this alkoxy group over here. Remember, oxygen's pretty electronegative, so instead of these electrons being sucked up by this carbonyl oxygen, this oxygen over here is also pulling some of that electron density this way. All right, and so that kind of destabilizes that single bond resonance structure, and that's, in other words, keeping this more in that double bond character. All right, so that's why we have a higher wave number here, because the single bond resonance structure is destabilized. Okay, and of course here you can see kind of a compromise between the two, right? You have that alkoxy group that's pulling the electron density away, but you also have a conjugated pi bond that helps contribute to that single bond character. All right, so notice that we have a wave number that's kind of in between these two options. Okay, let's talk a little bit about the intensity of the signals, right? So I pointed out that you could have very strong signals that absorb a lot of your IR radiation, right? And so they show up as a very deep peak, or you could have weak signals that are very shallow peaks. Okay, they don't have as much, they don't absorb as much of that infrared radiation. So what causes that? Well, again, now to think of this, you've got to go back to how the waves themselves work, right? So if you picture your bond as kind of as oscillating, as kind of like stretching vibration, okay, where you're going in between two sort of states, right? You could look at that interaction with the you could think of the dipole moment also oscillating with this stretch, with this sort of movement between your two atoms, right? So let's think back about how dipole moments work. So remember, your dipole moment, represented with the Greek letter mu, is it comes about by taking the partial charges, right? So you're dealing with the charge E times the distance between your two atoms, right? So in other words, this magnetic field is going to fluctuate as the distance between the two atoms increases and decreases, right? So as the atoms get further away from each other, as you stretch out that bond, you're going to increase that dipole moment, and then you're going to have them, and you also have it decrease as they get closer together, as that bond squeezes closer. All right. So what happens then is you have an electrical field that gets created by this oscillating dipole moment. Okay. Now, what affects that field, of course, then is how polar that bond is, right? The greater your dipole moment, the greater that oscillation and the greater the induced electrical field, right? So in other words, the greater your bond polarity, the stronger that IR signal, because the greater that electric field that gets created, and therefore its interaction with the IR radiation. Okay, so in a nutshell, the more polar your bond, the stronger your signal. That's really what it comes down to. Okay, so you can see here we have this very polar carbonyl, and that shows, we have that very electronegative oxygen compared to the not very electronegative carbon. And you can see that we have this very deep, strong signal. Whereas here we have this relatively non-polar carbon-carbon double bond, right? And carbons have the same electronegativity. Okay, so we have a relatively weak signal. Now, the fact that a signal shows up at all tells you that there is some polarity there. Okay, so it kind of depends on what groups we have attached to these four bonds. Clearly, they're not the same. If you do have a completely symmetrical molecule, it's completely nonpolar, well, then you're going to have a dipole moment of 0, which then means that there's no electrical field and there's therefore no interaction with your infrared radiation, and you actually don't see a signal. All right. So normally you would expect a carbon-carbon double bond to show up somewhere in this range, right, between 1600 and 1700. But if we had a completely nonpolar molecule, so try drawing out 2,3-dimethyl-2-butene, all right, it's going to be actually, I guess I could just draw it out to show you. Basically, if we have 2 butenes, so 1, 2, 3, 4. Okay. And so if we have a double methyl group at the number 2 position and methyl group at the number 3 position, you can see that this molecule is completely nonpolar, right? And therefore, there won't be any signal at all from that carbon-carbon double bond. Now, you're probably saying to yourself, wait a minute, there are a lot of carbon-hydrogen bonds here. Those aren't very polar. Why do we get significant signals for those if, nonpolar stretches don't really show up very well? Well, there's kind of a combined effect here. It's kind of like how you can get even though like London dispersion forces are really weak forces between nonpolar molecules, if you have enough electron density, if you have a large and squishy enough molecule, it'll have its molecules will form a solid, right? They'll have a high enough melting point or boiling point, than you would expect for something that has only London dispersion forces. So this is kind of a similar concept, that if you have a lot of carbon-hydrogen bonds, which often is the case, you will still get a decent signal, even though those bonds themselves are actually nonpolar. Finally, we come to signal shape. So basically, whether a signal is broad versus narrow, right? So we've seen in an example with an alcohol group that we get a very broad peak for that. So why is it? What is it about that alcohol group that gives us that broad signal that we observe? Well, it comes down to the hydrogen bonding that we saw. So the oxygen-hydrogen bond of our alcohol group is actually kind of stretched out due to the hydrogen bonding that occurs between that hydrogen of that alcohol group with another alcohol. All right, so basically that the ability of that that sort of stretching out of that bond, that weakening of that bond because of the attraction of that hydrogen to another alcohol group is what causes that broadening. So you can actually play around with this to sort of confirm the presence of one of these sort of labile hydrogens. If you use a solvent that prevents hydrogen bonding, you would see that this what would normally be a broad peak would become very narrow. And there you would then know that that would confirm that you are dealing with something that normally would have hydrogen bonding. So here's an example of that. So while you normally would have this very broad OH peak here, if you do have a sample of an alcohol that that doesn't have hydrogen bonding mixed in there, or you've limited the amount of hydrogen bonding here, you'll see this narrow peak from your OH groups that aren't engaging in hydrogen bonding. Okay, now we've seen that broad peak from alcohol groups. Another scenario that you often see in these IRs is a carboxylic acid. Now, in the case of a carboxylic acid, not only do you have that hydrogen bonding affecting that OH bond, but also the resonance with that carbonyl group. So this causes a really broad peak for that OH bond. All right, so you notice that we have instead of just that regular broad peak we would see for an alcohol group, we had this huge broad peak over here. And this is kind of a telltale sign for carboxylic acids in general. So something to keep in mind when you're trying to read a spectrum. If you see a huge peak like this that takes up like almost a third of your spectrum, it's kind of indicative that there's a carboxylic acid. Right? In addition to the resonance, the other reason that this is so pronounced is also the way your two carboxylic acid molecules will dimerize. So it just kind of, you kind of see an increased amount of hydrogen bonding that way. Okay, so let's practice this. Go ahead and pause this video and see if you can predict the types of stretches you would observe for this molecule over here. All right, so if you've come back after having paused this video, hopefully you should have picked these up. So notice that we have a carboxylic acid group here. We have a carbon-carbon double bond here. Okay, and so think about not only just those functional groups, but also some of the hydrogens attached to those, right? So you've got to consider that we have regular sp3 carbon-hydrogen stretches, but we also have carbon-hydrogen bonds attached to these sp2 carbons, or rather just this sp2 carbon. And so keep in mind that that would show up just above 3,000 as opposed to below 3,000. Okay. Of course, I pointed out just now that this OH stretch is going to be really, really broad. Don't forget, we also have our carbonyl stretch. Okay, that would show up there around 1,700. And I think that covers about everything. Okay, but again, if you were looking at this, I think this OH stretch here would be really, would kind of really point out that you're dealing with a carboxylic acid. Okay, but that being said, if you want to distinguish between multiple carboxylic acids, you want to take into account all of these peaks that would show up. All right. So another thing to consider when it comes to the number of stretches you see due to in this region where you have an electronegative atom attached to a hydrogen is the nitrogen-hydrogen stretches that we see in primary and secondary amines. All right, so this is another piece of information we can get here that's very useful when trying to discern information out of IR spectra. Now, in the case of amines, of course, why don't we see tertiary amines? Remember, tertiary amines don't have any hydrogens attached to them, right? We have only 3 alkyl groups attached to our nitrogen, so you wouldn't see an NH stretch. Now, how can we distinguish between a primary versus a secondary amine? Well, first of all, you know that it's going to be you'd see a pretty strong signal due to the electronegativity of that nitrogen causing, that bond to be relatively polar. Now, of course, it won't be as polar or as strong a signal as an alcohol group, but still, again, you'd see a significant peak. Now, how many peaks do you see? This is the key difference between a primary and secondary amine. So here's an example. All right. Again, notice that it's not as, if this was an alcohol group, it'd be much deeper, a much stronger signal. But again, pretty significant here, right? Notice that here we have a primary amine, and we see 2 peaks at about the same, around the same wave numbers. And for our secondary amine, which has only 1 hydrogen, we have only 1 peak. Okay, so ask yourself, why is that? Now, the answer that's immediately coming to your mind is actually wrong. You're probably saying to yourself, well, obviously there's 2 hydrogens here. That's why we see 2 signals. That's actually not the reason why you see 2 signals. It's because there are 2 types of stretches that we observe. So in the case of a primary amine with its 2 hydrogens, you have a symmetric stretch where both of these hydrogens move in and out together. All right. And you could have an asymmetric stretch where they alternate. So this one's coming in as this one's going out, and then as this one comes in, this one goes out. Okay, so both of those types of stretches give different signals. In the case of a secondary amine, which has only 1 hydrogen, you really don't have a difference between symmetric or asymmetric. There's only 1 hydrogen that's moving back and forth, and that's why you only see 1 signal for that one. Okay. This phenomenon is also, applies to other groups of, bonds between hydrogen and other atoms. So for example, if you have methylene or methyl groups, this effect also comes into play. That being said, since we're usually dealing with a lot of these carbon-hydrogen bonds, typically it kind of gets lost in the shuffle. So it's probably not as obvious as with a primary versus secondary amine, which has, a pretty strong signal, a pretty broad signal, and therefore it's a little bit easier to observe. So something to keep in mind when you're trying to distinguish between 2 amines. All right. So if you have a primary versus secondary amine, look for that where that nitrogen hydrogen stretch should show up. Relatively to the left of your spectrum, and look for 1 or 2 signals. And of course, if you don't see a signal there at all, even though you know your molecule is an amine, that might be a hint that you're actually dealing with a tertiary amine. Okay, so something to keep in mind when you're looking for amines there. Okay, so let's summarize everything we've learned from that. Okay, so when you're looking at an IR spectrum, as I pointed out earlier, you want to focus on the diagnostic region. The fingerprint region, it's usually just a huge mess of peaks. You're not going to get a lot of good, meaningful information there. So kind of focus more on the diagnostic region above 1500 wave numbers. Okay, so remember, break it down to sections. Right? So you have a section for double bonds, you have a section for triple bonds, and then you have a section for bonds of things to hydrogen. Okay. Of course, other single bonds will be down in the fingerprint region where, we can't really get a lot of good information out of that. But for things bonded to hydrogen, those will show up way to the left above 2700 wave numbers. Then once you've looked at those wave numbers, okay, and figured out which sections they belong to and that helps break them down, also, consider the intensity of the peaks, all right? So why are they strong signals? Are they relatively weak signals? And that tells you something about the polarity of the molecules, or at least those bonds. And then, of course, look at the shape. Are they a broad peak or a narrow peak? Okay, and again, that tells you something about the potential for hydrogen bonding. Okay, so let's have a look over here. So when we look in that carbon-hydrogen region here, of course, it might also help to have, to mark that 3000 number there. Because remember, any peaks below that are hydrogens attached to a sp3 hybridized carbon. If you see any peaks just a little bit beyond that, okay, so between somewhere around 3100 versus 3200, again, note that you're dealing with sp2 versus sp3 carbons. Again, not the carbons themselves, but specifically with hydrogens attached to them. Okay, so if you have an if let's say you have an internal alkyne, you're not going to see a peak here because there's no hydrogen attached to that sp hybridized carbon. Okay, and of course, once you get even further downfield, you have like amines and alcohol groups. Okay, and of course, like I said, you'll the broadness of those peaks also tell you something. Okay, so I pointed out earlier in this chapter that one of the key things for IR is to help identify functional groups. Now, why is that useful? Well, oftentimes when we're doing reactions, when we're carrying out multi-step syntheses, we're changing our functional group. Okay, so and running a quick IR might tell you a lot of information in that respect. So for example, let's say we are oxidizing this alcohol over here into the corresponding ketone. Well, running an IR would quickly tell you whether or not you made this product. Okay, so again, think about the difference between that alcohol functional group and how it would show up versus that ketone functional group. Okay, so remember, this is a carbon-oxygen double bond, so that'll show up in a set place in your spectrum. More importantly, that really broad peak that you would normally see all the way to the left for your alcohol group, that would disappear. Okay, so that would tell you that your reaction happened. Okay, your alcohol group was converted into something else. Okay, go ahead and pause this video for a second, and while you're doing that, have a look at these different reactions and ask yourself, how could IR data help you verify that the reaction happened? Okay, so if you've joined us back again, I don't actually have an answer slide for this, so I'll just walk through each of these answers together. So if we look at this one over here, notice that we have an alkene and it's moving, right? So we don't have really any other functional groups. So the functional groups themselves haven't changed. So what are we looking for that's different? What peaks might appear or disappear? Well, what's attached to that alkene? Well, remember, we're looking, like obviously both these will have carbon double bond stretches, so that might not tell us anything. But what other peaks might we see? Well, over here, we're going to have a carbon-hydrogen stretch that will show up above 3000 wave numbers because it's attached to an sp2 carbon. What about over here? Well, this alkene is tetrasubstituted, so we don't have any hydrogens here. So that carbon-hydrogen stretch above 3000 would disappear. Okay, and that would show that we've made this product. Okay, and then what about this reaction here? Well, now we've gotten rid of this carbon-carbon double bond, which, of course, would be a very weak signal. Notice that this is a relatively nonpolar molecule. Instead, over here, we have carbon-oxygen double bonds. Those would show up as a pretty strong signal, right, due to the polarity of that carbonyl. So that's the difference there. We would see a strong signal popping up in that carbonyl range. Okay. Now, again, this is a very qualitative analysis. It just tells us the presence or absence of these functional groups. It doesn't tell us how much of your product has been made. It won't tell you what your yield is, for example. Okay, you have to use some more quantitative methods to figure that out. All right. So that's it for IR, for infrared. Let's move on to mass spectrometry. Okay, mass spectrometry is also another one of those fundamental techniques that we use to characterize a material. So, as the name suggests, it tells us information about the mass of our substance, or rather pieces of our molecule that we're dealing with. So what happens here is basically our sample is vaporized, and in the process it is ionized. It's converted into a positively charged ion that then gets attracted to a negative electrode near the detector. Now, based on the mass of this ion, it will get deflected a certain amount as it makes its way to the detector. So based on where it hits the detector, the machine will tell you how heavy that fragment is. Okay, so let's look at that in a little bit more detail. So the most common way to ionize these molecules is to bombard them with electrons. So you fire electrons at them, and that in turn strips away electrons. So it causes your molecule to break apart into what's called a radical cation. In other words, you take away an electron, now you have an unpaired electron, that's the radical part, and because you've taken away a negative electron, the what you have left behind from your molecule is now positively charged, and that's the cation part. Okay, so now you've taken away an electron from your original molecule. Now, electrons are very light, right? They're kind of insignificant when it comes to the mass of the overall mass you're dealing with, right? Protons and neutrons are about 1 atomic mass unit. Electrons are kind of next to negligible there. So if we've taken away an electron, what's left behind is basically still the mass of your original molecule. Okay, if this radical cation is relatively intact here, we call this a parent ion. So in other words, if this fragment, this pretty much intact fragment, hits the detector, that mass is effectively the mass of your original molecule. So looking for this parent ion in your data is usually very helpful. Now, that being said, oftentimes your molecule will fragment further. It'll break apart into smaller pieces as your radical cation tries to become more stable. Okay, so for example, here we can have an electron from our radical transfer over to one atom, and we can see that our radical cation breaks apart into a radical and a carbocation, right? So now, which of these will hit the detector? Well, your carbocation is what's going to make its way towards the detector, and because it's still charged, and therefore it will not, it's what's going to show up in your data. Okay, the radical won't. Okay. So when we look at our data, this is kind of what it looks like. You'll see a bunch of peaks. On your x-axis, you have what's called the m to z ratio. In other words, the mass per unit charge of your fragments. Okay. On the y-axis, you have what's called the relative abundance. In other words, how many of these particles are hitting your detector. All right, so that tells you how common are these fragments. So typically, the largest, heaviest peak, so towards the right of your graph, that's usually your parent ion, and so that kind of tells you what you are, what was your original molecule, basically, right? And we represent this with the symbol M plus dot. Again, remember, this is a radical cation, right? Hence the radical symbol, that dot over there for the unpaired electron, and the cation is represented, of course, with a positive charge. Okay, and we use a capital M to represent that parent molecule. So that is our parent ion peak, and again, notice that here for methane, it's at 16, m/z, which makes sense that a molecule of methane weighs 16 atomic mass units. Now, you're probably wondering, what about that peak over here that's at 17 atomic mass units? That's not going to be the parent ion. That's the m+1 peak. We'll talk about that a little bit later. Okay, we'll get into that in a little bit. Okay, let's talk a little bit about fragmentation. So you probably noticed that there were peaks below 16 in that graph I just had for methane. So why is that? Well, that's where that fragmentation comes in. So if you have your parent ion, right, that radical cation here, and in the process we lose a hydrogen radical, well, that resulting methyl carbocation gives us that peak that we saw at 15. Likewise, you can keep on fragmenting off hydrogens, and we will see peaks at, accordingly at 12, 13, and 14. At 12, we're dealing with just a carbon atom, okay, rather a positively charged carbon atom. Okay, so that's where we kind of get into that. I pointed out that mass spec is kind of a very common analytical method. It's one of the key things we use for characterizing a molecule that we've made. So if any of you go into research, especially if you go into like synthetic organic chemistry, if you ever make a molecule, something that's relatively original, part of documenting it is getting just this fundamental data about it, including things like mass spec, IR, NMR, all of this stuff, just to help, analyze it or to catalog it. Okay, so how do we read the data from our mass spec? Okay, as I pointed out earlier, that parent ion peak is kind of really important, right? It kind of gives you an idea of what is your original molecule that's not fragmented, which is kind of what you really want to get out of this. Though, of course, a little bit of information about how that molecule fragments can tell you a little bit about the pieces that make up the molecule. In other words, its shape, its structure. Though, of course, you're kind of limited here in that kind of analysis. Typically, you want to use something like NMR to do that, but you can still get some information out of mass spec. Okay. Anywho, so here we have benzene, a molecule that doesn't really easily fragment. So you can see that we have, in terms of all of our fragment peaks, they're relatively short. But this parent ion peak over here at 78 tells us that, well, that makes sense. It corresponds to the molar mass of our benzene. Okay, now here we have hexane, right? Or sorry, pentane. And you can see that we have a lot of fragmentation. In fact, the most abundant peak over here is somewhere in the middle, though that's not our parent ion. Our parent ion peak is down here at 72. Okay, which again, that 72 tells us that we have, that's the mass of your full molecule. That being said, we can still get some useful information here, right? If we look at the higher peaks as we move down into these little clusters, you'll notice that they correspond to the loss of, let's say, a methyl group or an ethyl group, and so on. Okay, so basically, like I said, the key thing you want to start off with is looking for your parent ion peak, right? Look for that highest value significant peak, and that tells you essentially the molar mass of your compound. Okay. Now there are other pieces of information you could glean from this. For example, if you have an odd number, it could potentially tell you that you have an odd number of nitrogen atoms, where an even number might tell you that you have an even number of nitrogen atoms, even no nitrogen atoms. That's not an amine at all. So again, that's just a potential piece of information you might have. In case you're wondering about that, that's because your nitrogen has, typically will have 3 bonds and a lone pair on it, which is an odd number, and as opposed to carbons, which tend to have even numbers of bonds connected to them, or oxygens for that matter, which also have an even number of bonds. So the presence of an odd number kind of gives away that you're dealing with a nitrogen. Okay. So I mentioned earlier that you sometimes have peaks that are beyond your parent ion peak, which on the face of it sounds really confusing, right? Why, if your parent ion represents the whole molecule, how are you adding something to your molecule, right? To get that M+1 peak, for example. Well, it's not that you're really adding anything, but you have to keep in mind that you're not dealing with average atomic masses here. You're dealing with regular atoms, things with protons and neutrons in just integers, right? You've got whole numbers you're dealing with here. So now we've got to take into account isotopes, right? So while carbon-12 is the most common isotope of carbon and therefore accounts for the parent ion peak you see, don't forget there are heavier isotopes of carbon out there. You have carbon-13, carbon-14, okay, out of which carbon-13 is significant enough that you will see a tiny peak based on the presence of carbon-13. You just are going to have some molecules in your sample that have a carbon-13 instead of a carbon-12. Okay, and that's where that peak comes from. All right, so whenever you see a peak beyond your parent ion, that's usually due to your to isotope effects. Okay, now the more carbons you have, the more likely you're going to come across carbon-13s. Carbon-13s make about 1% of all the carbon you're dealing with. So as you increase the number of carbons, you increase the probability that there are going to be carbon-13s present. Okay, so that's why if we have a larger molecule like decane, which has 10 carbons, notice that our M+1 peak is much more significant than, if we go back here, you can see how small that peak is for methane, which has only 1 carbon. Okay, so that's something to keep in mind when you're trying to analyze that M+1 peak. Okay, again though, this is only possible because that carbon-13 makes up 1% of carbon. Now that doesn't sound like a large number, but when we're dealing with isotopes here, that's still significant. Okay, so something like the hydrogens that we deal with are going to be mostly hydrogen 1, but you don't really see M+1 peaks for hydrogen 2 or hydrogen 3 because their percentages are so low. All right, now that being said, there are other isotope effects you want to keep in mind, and those also give away some telltale signs for molecules you're dealing with, or at least atoms within your molecules. So, for example, chlorine has a very interesting isotopic ratio. Chlorine is mostly made up of chlorine-35 and chlorine-37, out of which about 3/4 of it is chlorine-35, and the remaining quarter is chlorine-37. So you will see a 1 to 3 ratio peak that are two numbers apart from each other, right? So basically, that if you see a set of peaks that look like this, that kind of gives away that there's a chlorine present in your molecule. Likewise, bromine has 2 major isotopes, bromine 79 and bromine 81, and they're about a 50-50 split. And so if you see 2 peaks that are relatively even, that are again 2 numbers apart, that usually is a telltale sign that you are dealing with a molecule that has a bromine in it. Okay, so again, when you're looking at your mass spec, keep an eye out for, when you're looking at that cluster of peaks near your parent ion, keep in mind the shape or the grouping together of peaks like that. Now, I mentioned earlier that when you have your molecule splitting apart into fragments, you can kind of tell, a little bit of information of the pieces making up that original molecule when you look at the clusters of fragments. Okay, so typically when you look at your clusters of peaks, the difference between them accounts for the splitting off of things like methyl groups or ethyl groups or so on. So you can see that, for example, here. In this case, we have pentane, and we had different sets of peaks. And if we looked at the masses in between them, you could see that after your parent ion, you might see a peak that is 15 numbers below your parent ion. Okay, and that accounts for the loss of a methyl group. Okay, likewise, you might see one that's 29 below your parent ion, and that accounts for the loss of an ethyl group that's being lost as a radical, and therefore doesn't show up in the detector. Okay, so when you look at the actual graph, you can see these sort of groupings of peaks likewise here. So here's that peak where you've got your fragment that has lost a methyl group, and here where it's lost an ethyl group, and so on. You can tell from this that the group that's lost the ethyl group is probably the most stable. out of all of those fragments. Okay. So typically that tells you a little bit about the stability of the fragments, but again, sometimes it's a little hard to interpret. So while you can get some meaningful information here, in the next chapter when we get to NMR, not only can you get information about these fragments, but also how they're connected to each other. That's going to be some really useful information there. Now, why do certain fragments have different stabilities? So this goes back to the sort of electron donating effect from our alkyl groups, right? So if you remember, due to hyperconjugation, that's the overlap of those carbon-hydrogen bonds with the empty p orbital on your carbocation, you have a certain stabilizing effect when your carbocation has an alkyl group attached to it. So tertiary carbocations are more stable than secondary carbocations, which are more stable than primary carbocations, which are more stable than a methyl group. Okay, so in this case, if we can get a tertiary carbocation through fragmentation, this would be your most abundant fragment that you'd see. Okay, and the fact that it is 43 below your parent ion tells you that there is a propyl group that's broken off here that was attached to that tertiary site. Okay, so again, that involves a little bit more analysis, and there are easier ways to do this, but that is meaningful information you could get out of your mass spec. Other types of stable fragments can come about through resonance. So one thing you might see pretty commonly in the case of alcohols is what's called alpha cleavage. So basically, if you break, so basically you have a cleavage between your alpha and beta carbon. So here's your alcohol group. Alpha carbon is attached to it. The beta carbon is one carbon away from that. If you break that bond, that radical unpaired electron comes down and forms a double bond here, which you can see makes a resonance stabilized carbocation, which is what shows up on your detector. Okay, so again, based on what's missing, you can kind of figure out, well, what was at that beta carbon onwards, right? That's what broke off and doesn't show up at your detector. Okay. Other common cleavage sites include alcohol groups breaking off to form water. So basically, if you have a hydrogen that's at that beta carbon, you can basically lose a water molecule in the process, and that water weighs 18 atomic mass units, so that accounts for that difference there. Okay, so in addition to alcohols, amines also do alpha cleavage. So that's another place that you might form a very stable fragment, okay, when you're dealing with an amine. Carbonyls also can undergo a rearrangement known as a McLafferty rearrangement, which makes a very stable molecule, resonance stabilized molecule here. Okay, so please note that over here, the cleavage occurs again between that alpha and beta carbon, though you need to lose a hydrogen on your gamma carbon accordingly for this to happen. Okay. All right, so in addition to just regular mass spec, it's possible to do what we call high-resolution mass spec. So not only do we just see that M to Z ratio, but we actually go to more significant figures. We measure up to 4 decimal places, and that really helps us nail down the difference in isotopes there. That's because protons and neutrons, while they are both approximately 1 atomic mass unit, are not exactly 1 atomic mass unit. So once we get down to those kinds of differences, down to 4 decimal places, we can really pick apart the difference between 2 different fragments or 2 different parent ions. All right. This gets really important when we're dealing with 2 potential molecules that we're trying to distinguish between, and they have similar atomic masses, or sorry, molecular masses. All right. So it comes down to the difference in the atomic masses of the atoms making them up. So for example, here we have cyclopentanone, right, which is a ketone, and here we have cyclohexane. Now, both of these have a molecular weight around 84 grams per mole, or 84 atomic mass units. So if you looked at the parent ions for these with low-res mass spec, you would see parent ions about 84. Okay, and both these molecules wouldn't really fragment very much, and if they did, they'd probably have similar types of fragments forming. So a low-res mass spec doesn't tell you a lot. However, carbon and oxygens have different masses once you get down to 4 decimal places. So you could really distinguish between your two parent ions once you get down to that level. Okay. So yeah, so basically, if we plug in the molar mass, the molecular weight of both these molecules down to 4 decimal places, you can see that our cyclopentanone is 84.0573 atomic mass units, whereas our cyclohexane is 84.0936 atomic mass units. And so looking for that parent ion, you'd be able to distinguish between those two. Another useful application of mass spec is actually in conjunction with another analytical technique, one that you may recall from last semester from the lab involving the dehydration of 2-methyl cyclohexanol. If you recall, when we do that elimination reaction, we get a mixture of 2 products. We get the 1-methyl cyclohexene and the 3-methyl cyclohexene. And we ran a GC, or gas chromatograph, on that mixture to kind of see the distribution of the 2 products, right? So if you go back through our labs from last semester, you might remember seeing a graph that had 2 peaks, with one peak bigger than the other, to show which one was your major product, which one was your minor product. A GC mass spec is basically taking these 2 techniques and running them together. So up until now, we've been looking at mass specs with just pure samples, right, with just one substance. But oftentimes, when you have a mixture of substances, it helps to separate them out using gas chromatography first. And then, of course, you can run a mass spec immediately on those. So if you've ever seen an episode of Law and Order, you've probably heard of this technique at some point. Anytime they cut to the forensics department, and whoever's working forensics down there is just like, oh yeah, I ran that sample through the GC mass spec, and it told me this, this, and this. This is the same instrument that they're using. Okay, so essentially you run a GC first, so it separates out your sample into the components making it up. All right, so you get a gas chromatograph, spectrum that chromatogram rather, that looks like this, that has these different peaks based on how your different components of your mixture travel through the column of your GC, and then you run a mass spec on that data accordingly. And so that gives you information about what each of those individual peaks corresponds to. Okay, so in the case of Law and Order, in the forensics, there when you have a mixture of a sample from a crime scene, it tells you what those individual peaks correspond to. So between how they move through the GC as well as the mass of your parent ion, you could probably identify a particular material. Okay, so for example, if you've got an arson crime scene, you could detect an accelerant. So for example, you could notice trace amounts of gasoline, for example, that tells you oh, this wasn't an accidental fire. This was someone dumped gasoline on this and they set the fire on purpose, for example. You might use it to look for particular drugs, for example, and so if you have a sample such as blood or urine, you could look for key markers, for whatever substance you're looking for. Okay, now another variation of mass spec that you might come across is electrospray ionization, or ESI. I mentioned earlier when we talked about how mass spec worked in general, I mentioned that we basically fire a beam of high energy electrons at our sample. It flakes off electrons, converts them into radical cations, and this is what makes its way through the detector. The problem with this is that when you subject your sample to such harsh conditions, you might degrade it. So in the case of certain samples, for example, certain proteins, large biomolecules in general, you can damage your sample and therefore not get any meaningful information if you try to do that. So instead, you need to find a milder way to ionize your sample. And to do that, we use what's called electrospray ionization. Okay, so essentially, you take your sample, all right, your liquid sample, and instead of ionizing it or vaporizing it using a lot of energy, you put it into a vacuum, and that kind of lowers the energy requirement to convert it into an ion spray. Okay, so basically, you instead of firing a beam of electrons, you use a high voltage needle in your evacuated sample to convert it into a form that will make its way towards the detector. All right, so that's it for mass spec and IR. So we're going to close out this chapter with one more piece of information when it comes to analyzing our sample or a compound and trying to figure out what it is, right? Because that's kind of the goal here, right? We want to use these analytical techniques to figure out what we've got in our sample. And you want, oftentimes you need more than one approach to solve the puzzle. All right, so you can have IR data that tells you what functional groups you're dealing with. You can use mass spec data that tells you what your parent ion weighs. But in addition to that, it might be helpful if you do happen to have a molecular formula. You can figure out the presence of double bonds or rings by looking for degrees of unsaturation. Okay, so what do I mean by degrees of unsaturation? If you recall from last semester when we looked at the difference between alkanes versus alkenes versus alkynes, this concept of saturated versus unsaturated hydrocarbons came up. So if you recall, alkanes are saturated hydrocarbons because they have the maximum number of hydrogens attached to their carbons. Alkanes don't have any double or triple bonds, right? Because that would imply that you could do a hydration or a hydrogenation reaction where you can add hydrogen across those double bonds and increase your number of hydrogens. Okay, so that's why alkenes and alkynes are known as unsaturated. There's room for extra hydrogens to go on there. So when we look at degrees of unsaturation, we're looking at how many extra hydrogens could we add to this molecule. And therefore, by seeing the room for hydrogens, we can kind of figure out, well, how many double bonds are there? Or how many places have we closed our chain of carbons into a ring? So to understand this, let's first look at that generic formula for an alkane. So for every carbon, we have double the number of hydrogens plus 2. Okay, plus 2 extra hydrogens. Now, where does that come from? Let's start off with a very simple example here. Let's look at propane, which has 3 carbons. So let's draw those 3 carbons in a row here. Okay, now if you remember, carbon wants to form 4 bonds. So if we look at that central carbon, it's got 2 of its bonds already taken up with bonds to the carbons on either side of it. So it needs just 2 more hydrogens to give it 4 bonds. Okay, so it's a little CH2 unit. Now, for the terminal carbons, okay, so if we look at this terminal carbon over here, it's only got 1 bond taken up with a carbon, so it's going to need 3 more bonds to give it 4 bonds to help it meet the octet rule. Now, you could think of that as being a CH2 unit, just like this internal carbon, but we just have to add an extra hydrogen to help it meet the octet. Okay. Likewise, this carbon over here at the end is another CH2 with an extra hydrogen. Okay, so we've essentially added these 2 extra hydrogens to our 2 terminal carbons. All right, and so that's where that formula comes in, right? So it's just the number of carbons. Since you've got these CH2 units repeating, that's why you have double the number of hydrogens, but you have 2 extra hydrogens because you need to cap off those terminal carbons with a hydrogen to help them meet the octet rule. Okay, so whenever you extend a carbon chain, all you're doing is you're adding CH2 units in the middle there. Your terminal carbons still wind up being CH3s. Okay, and therefore this formula holds true. So for propane here, you have 3 carbons. 3 times 2 is 6. Okay, so those are the 6 carbons here, plus your 2 terminal carbons gives you 8. So that's why the formula of propane is C3H8. Okay, if you were to try this out with butane, all right, with butane you would have 4 carbons. Okay, well, that formula, if you double 4, you get 8 plus 2, there's 10 hydrogens. Okay, so if you try drawing out butane, you would notice that the formula would still be C4H10. Okay, we could try this out with pentane as well. All right, and actually drawing out pentane, isomers of pentane, will give you a feel for why this, you still have the same formula for the same pattern, even if you are dealing with a branched alkane. So, for example, let's say we had 2-methyl butane. All right, so I mentioned earlier that butane is going to be C4H10, right? So if I have 4 carbons, okay, so a regular butane, I have, if I just add in each of these bonds, so I've got 4 carbons, so I've got 4 of those CH2 units, okay? Really, it's just my internal ones are CH2s, but if I look at my 2 terminal ones at the end, those are CH2s plus the 2 extra hydrogens, okay? So again, following that formula, that's C4H, 4 times 2 is 8, 8 plus 2 is 10, and if you count this, you'll see there are 10 hydrogens, okay? Let me just make a note of this here so that we have that when you're checking that out later. Okay, if we were to try to branch this out, let's say we had 2-methyl propane. Okay, so for that, we would have a methyl group coming off that number 2 carbon here. Okay, so let's look at the number of hydrogens for a molecule like this. Okay, again, each of these carbons needs to have 4 bonds. So we have, let's say we have 2 hydrogens here, plus the third one to give that 4. Again, CH2 like that, there. And if we look at this methyl group over here, if we consider that as a CH2 group, it needs another hydrogen here. Now we've got 3 terminal hydrogens. But keep in mind that this internal carbon here, instead of being a CH2 unit, has one of its bonds taken up with that methyl group. So instead of having 2 hydrogens, it has only 1 hydrogen. That extra hydrogen goes to that branch. Okay, so if you count the number of hydrogens in this formula is still C4H10, and it's still following that format where your number of carbons is doubled plus 2. Okay, so go ahead and try this out with pentane. Give this a shot. Like, pause this video, and then on the next slide, I have just the skeletal structures of different isomers of pentane, and you can verify that all of them are going to be C5H12. Okay, so anytime you have a saturated hydrocarbon, that's going to be the case. Okay, so here are our different isomers of pentane, and I've drawn them as skeletal structures, but if you want to draw them as condensed structural formulas or even like regular Lewis structures, you can confirm that they're going to have the formula C5H12. Okay, again, going off that pattern where 5 doubled is 10, 10 plus 2 is 12, and that's the number of hydrogens you have for a saturated hydrocarbon. So, where we can figure out degrees of unsaturation comes in from where this formula deviates from that pattern. So pentane has the formula C5H12, but let's say we had 5 carbons, but fewer than 12 hydrogens. For example, here we have a double bond. Okay, we've got an alkene. Notice that in doing so, our formula drops down to C5H10. Okay, that double bond is a degree of unsaturation, or has a degree of unsaturation. Now, over here, the formula would be C5H8. That's because this triple bond, okay, which has 2 pi bonds in there, has 2 degrees of unsaturation. Okay, now once you start getting multiple degrees of unsaturation, you'll see that there are ways to play around with this. In this case, we have a triple bond, but it's possible to also have 2 double bonds. In both cases, you have 2 pi bonds, which would still give you that formula C5H8. All right, so you're kind of limited in how much information you can get out of this, but still, that's meaningful information. All right. Now, why don't you try that out with something like cyclopentane? This gives you a good idea of how this also applies to ring compounds. Draw out cyclopentane and ask yourself what's the formula going to be, and how does it deviate from our generic alkane formula here. Okay, so if you draw that out, you've probably noticed that, if you draw cyclopentane, we've got 5 carbons in a ring, and each of them are CH2 units. So in other words, this formula is going to be C5H10. So notice that that's 10 and not 12. So closing a ring adds a degree of unsaturation. Okay, so if you had the formula C5H10, it could imply that there's either a double bond in there or there is a ring in there. Okay, but not both. So that's something to keep in mind when you have the molecular formula for a molecule you're trying to figure out the structural formula of. Okay, so let's have a look at an example here. Let's say we have C4H6. Well, if you've got 4 carbons, how many hydrogens would there be if it were saturated? Well, 4 times 2 is 8. 8 plus 2 is 10. So there should be 10 hydrogens, but instead of 10 hydrogens, there's only 6. Okay, so you're 4 hydrogens short. Now remember, you add on 2 hydrogens for, let's say, every double bond or every ring that you close. So there are 2 degrees of unsaturation. Now, what does that mean? Well, there's lots of possibilities. You could have 2 double bonds, you could have a triple bond, you could have 2 rings, or you could have a ring and a double bond. Okay, so there's lots of possibilities here. You're kind of limited in how much information you get out of this, but it's still meaningful information. All right. Now, in addition to rings and pi bonds, there are other pieces of information we can get from other like heteroatoms. Okay, so for example, if we have a halogen, because halogens like to form a bond, just one bond, just like hydrogen, you can kind of swap out halogens for hydrogens. So in this case of chloroethane versus regular ethane, you can see that we still have 6 non-carbon atoms in our molecule. Okay, whether they're all hydrogens in the case of ethane versus 5 hydrogens and 1 chlorine in the case of chloroethane. Okay, and notice this has no degrees of unsaturation then if you treat a chlorine as a hydrogen. Okay, which again makes sense. There's no double bonds, no rings, nothing like that. So let's try that out. Here we have a molecule C5H9Br. Okay, are there any degrees of unsaturation in that? Well, treat that bromine as if it's a hydrogen. So instead of 9 hydrogens, pretend we've got 10 hydrogens. How many hydrogens should we have if there are 5 carbons? Well, 5 times 2 is 10. 10 plus 5 times 2 is 10. 10 plus 2 is 12. There should have been 12 hydrogens, or hydrogens and halogens, if this were completely saturated. So the fact that there's only 10 of those tells you that there's 1 degree of unsaturation. Okay, so there's either a double bond or a ring somewhere in that molecule. Okay, another heteroatom that doesn't affect your HDI is oxygen. Oxygen forms 2 bonds and has 2 lone pairs, but basically you could kind of think of it as being inserted between a carbon and a hydrogen. Okay, so notice that if we take the oxygen out, we still have 6 hydrogens, whether we have ethanol here, which has the oxygen inserted, versus ethane, which obviously is missing the oxygen. Okay, in both cases, we have 6 hydrogens. Okay. In the case of a nitrogen, nitrogen increases your number of hydrogens by 1. Okay, so notice that without the nitrogen, we have 6 hydrogens in our ethane. As soon as you turn this into ethylamine, notice that in order for that nitrogen to have 3 bonds, you get an extra hydrogen. Right? We have 7 hydrogens in this molecule now. Okay, so that's something to keep in mind if you have a nitrogen in your molecular formula. If you have a saturated compound, it's going to have 1 more hydrogen than you would expect. Okay, so let's try that again with an example. Look at C5H8Br(N) and ask yourself, how many degrees of unsaturation are there in this molecule? Okay, well, if there are 5 carbons, there should be double that plus 2, so 10 plus 2 is 12 hydrogens, out of which we've got 8 hydrogens. We can treat that bromine as a 9th hydrogen, and keep in mind that the nitrogen means that you should have an extra hydrogen. So instead of 12 hydrogens, there should actually be 13. Okay, so instead of 13 hydrogens, we have only 9, if we treat that bromine like a hydrogen, so we're off by 4. So that tells us that there are 2 degrees of unsaturation. Okay, so instead of 4, we're missing 4 hydrogens, so to speak. That would have given us the right number, and therefore there must be either 2 pi bonds or a pi bond and a ring somewhere in our molecule, okay, for that to work out. Okay, so that's how you would work through it kind of in a step-by-step format. If you'd like, you could also just memorize this formula. Basically, using this formula, you can figure out your degrees of unsaturation by taking your number of carbons and doubling it, and adding 2. Okay, and then taking your number of nitrogens, because remember that adds in the hydrogens you need. And then subtracting your numbers of hydrogens and halogens, okay, and whatever difference there is, divide that by 2. Okay, so if there's no difference, then that tells you that you have a completely saturated hydrocarbon. Okay, but as soon as you start noticing there's an imbalance between your numbers of hydrogens and halogens versus the number that you're expecting, divide that by 2, all right? Because remember, there's 2 hydrogens for every degree of unsaturation, and that tells you how many degrees of unsaturation there are. Okay, so again, if you have lots of degrees of unsaturation, you're kind of limited in how useful that can be, because there's a lot of variation for possible results there. But again, sometimes that can be useful. Especially if you, for example, have a index of 0 that tells you there are no rings, there's no double bonds, no triple bonds, or anything like that. Okay, so let's practice this. Let's kind of combine multiple analytical methods here. So we have a formula of C7H12O, and we also are told that the IR for this molecule has a peak at 1687 wave numbers, and it also points out there are no IR peaks above 3000 wave numbers. Okay, so first of all, figure out how many degrees of unsaturation there are here, and then think about what these 2 pieces of information tell us about how the pieces of this molecule are connected together. Okay, so feel free to pause this video while you think about that. Okay, so first of all, let's figure out the degrees of unsaturation. Remember, oxygen has no effect on the degrees of unsaturation, so we can just look at our 7 carbons and ask ourselves, are 12 hydrogens enough to saturate those 7 carbons? And the answer is no, right? Because 7 times 2 is 14. 14 plus 2 is 16. So there should have been 16 hydrogens if this were a saturated molecule, but instead there is only 12, which means we're 4 hydrogens short, which means there are 2 degrees of unsaturation. Okay, so this could mean a ring, this could mean some combination of a ring or a pi bond, or in fact 2 pi bonds. Okay, so we have 2 degrees of unsaturation we've got to account for. What information does our IR tell us? This actually helps us narrow down our possibilities, right? If we look at this first piece of information from our IR, it actually does tell us that out of all those possibilities for 2 degrees of unsaturation, there's really only one thing that matches. If you recall, a carbonyl stretch shows up somewhere around 1700 wave numbers, right? Maybe a little bit more. Like a regular ketone should be like around, I don't know, 1720, somewhere in that ballpark. But if we have a conjugated ketone, that wave number drops to somewhere in that 1680 region due to that increased partial single bond character of that carbonyl. Okay, so the fact that we have a strong peak here at in that ballpark, the strong part tells you it's a polar bond. Okay, so that tells you, that carbon and oxygen must have a double bond. Okay, and that accounts for one of our degrees of unsaturation. But the fact that it's not above 1700, it's below 1700, tells us that there must be a conjugated pi bond next to it. So we have a pi bond that is, 2 bonds away from our carbonyl. Okay, so in other words, we know that if we have our ketone here, we have a double bond next to it. Okay, so that's what this tells us. What else do we know? Well, the second piece of information from our IR tells us that there are no IR peaks above 3000. So remember, that 3000 ballpark tells you about carbon-hydrogen stretches that have your hydrogen attached to either sp3, sp2, or sp hybridized carbons. If your carbon-hydrogen stretches are below 3000, that means it's attached to an sp3 carbon. If it's above 3000, it's attached to a sp2 or sp hybridized carbon. Now, look at our alkene, right? Those 2 carbons are sp2 hybridized. So, the fact that there are no peaks above 3000 tells you that there must be no hydrogens attached to those. Those must have only carbons. So, let's draw in carbons there. So there, and there, and there. And let's figure out now what do we have for our for our number of carbons. Are we have we accounted for everything? Oh, and don't forget this carbonyl over here, because that's an sp2 hybridized carbon as well, so there can't be a hydrogen here, otherwise that would also show up. So let's put a carbon there as well. So that gives us 1, 2, 3, 4, 5, 6, 7 carbons. So we've accounted for the 7 carbons in our formula. Okay, we've got our 2 degrees of unsaturation. If we count our number of hydrogens here, you should see that we have 12 hydrogens. Okay, so it's 3, 3, 3, and 3 here. So all those methyl groups add up to 12 hydrogens, and that should be our molecule. Okay, so even though we had relatively little information here, it's enough to kind of piece together something as complex as this molecule over here. All right, so that's kind of what it comes down to. You're given clues and you're solving a puzzle. So this can be kind of one of those, for those of you who like solving puzzles, this is kind of the more fun aspects of organic chemistry. And that's it for this chapter. So again, we're going to use the next couple of chapters in addition to this one to get more tools that we're going to add to our analytical toolkit that we're going to use to help piece together puzzles and solve them to figure out what an unknown molecule might be. All right, but for now, let's go through a couple of practice problems here. So explain why a completely nonpolar bond will not give a stretching signal in the IR spectra, and would you expect to see a signal for a carbon-hydrogen stretch in a nonpolar molecule? So to think back to signal strengths, you've got to go back to that section where we talk about that. But remember, it comes down to dipole moments. If a bond is completely nonpolar, it doesn't show up, right? There's no dipole moment, and therefore there's no signal that arises from that. Now, that being said, is a individual bond within a nonpolar molecule polar enough then to give rise to a signal? Okay, that's what it comes down to. You can have a molecule that is non-polar, but if the bonds themselves are polar, they will have a dipole moment and they will give a signal. Okay, so now in the case of a carbon-hydrogen stretch, I think that would be polar enough to give rise to the signal. Okay, so it might not be a very strong signal. Again, if you have lots of carbon-hydrogen stretches, they may add up, but this could be, it kind of depends, but basically it should be polar enough to give you a signal. Okay, explain how IR might be used to qualitatively determine the degree of substitution when ammonia is treated with excess bromoethane. So by degree of substitution, so if you have ammonia, which is NH3, you're swapping out those hydrogens with bromines, right? With ethyl groups, and you're going to basically produce an ethylamine plus HBr. Okay, and for every equivalent of bromoethane you add on, you're swapping out another hydrogen for an ethyl group. Well, so in other words, you're going from ammonia, which is NH3, to ethylamine, right, which is a primary amine, so there's two hydrogens on that nitrogen, to diethylamine, which is a secondary amine, which means it only has one hydrogen, and then finally you get triethylamine, which has no hydrogens on that nitrogen. It's a tertiary amine. Okay, now think back to where we looked at the types of stretches we'd expect to see for an amine. So, of course, that nitrogen-hydrogen bonds are pretty polar. They show up way to the left of your IR spectrum. Okay, they're going to be a little broad because they're capable of hydrogen bonding. But more importantly, the number of stretches tells us the type of amine we're dealing with because we have different types of stretches. Okay, so if you have a primary amine which has two hydrogens, we would see two signals. We would see a symmetrical versus an asymmetrical stretch. Okay, if you have a secondary amine, there's only one hydrogen, which means you'd only see one type of stretch, just that hydrogen going in and out. And then finally, if you have a tertiary amine, there would be no peak in that region because there's no nitrogen-hydrogen bonds to see. Okay, and I guess I kind of stopped at a tertiary amine. The question goes on to talk about quaternary ammonium salts. If in that case, again, you still have the same problem. There's no hydrogens on your nitrogen, and therefore that signal does not show up. Okay, how would you use GCMS to distinguish between constitutional isomers? Well, this is kind of a broad question, but basically, typically you have different, boiling points and different physical properties like polarity and so on. So the GC part of that would help distinguish that, just because based on the difference in polarity or boiling point, they would move through the column at different speeds. So they would show up as different peaks on your GC data. That being said, based on the fragmentation pattern of your mass spec, you could also try and piece together how those fragments are different. This is assuming, of course, that you are going to have different fragments. It's possible to have two constitutional isomers that have similar fragments, they're just arranged differently. So again, this is kind of a broad question. So, okay, explain how an experiment involving isotopic labeling might be useful to explore the type of fragmentation that occurs in the mass spec analysis. Again, it depends on the type of fragments you get, but if you're using a specific isotope and you're enriching your sample with that isotope, you want to look for that cluster of fragments where that isotope peak will show up. Okay, so for example, let's say using oxygen 18, you'd see a peak that would be an M+2 peak, right? Depending on where it shows up, you can kind of figure out, what fragment has that oxygen. You could also look for that oxygen to be missing. Keep in mind, it could be in the radical part of your fragmentation that doesn't show up at the detector. So instead of looking for a peak that has two mass numbers this two mass numbers higher, you might be looking for a drop in, 18 atomic mass units. Okay, so here's an example of where they've done that. You've got two places to put that that isotope of oxygen, and so based on the location of the oxygen, you get different fragments, right? So you can get, a fragment that's 31 versus 95, or you get a 33 versus 93, and so doing that, changing that location of that oxygen can help you figure out, or at least confirm, where that it's fragmenting at this bond over here. Okay. All right. So these practice problems have all been, a little bit more sort of theoretical, just helping you understand the concepts behind what we've learned today. In order to get ready for a quiz or exam, I recommend to try out the practice problems I've listed over on Blackboard. So typically on a quiz or exam, the way you'll see these types of problems laid out is you will actually have to sort of practice the concepts, or apply the concepts rather. So for example, you might be given an IR or a mass spec, and your answer choices will be potential molecules that fit that data. Or vice versa, you might have a molecule or molecular formula given to you, and you need to determine what peaks you might expect in an IR or mass spec. Okay, and those would be the answer choices given to you. So I think that would be a little bit more practical for you guys to get ready for a quiz or exam, rather than these additional practice problems that were in this PowerPoint. Okay, so be sure to check those out over on Blackboard for the list of homework problems or suggested homework problems. And of course, don't forget the solutions manual is available in the bookstore, in the library under the reference desk. And I've also uploaded digitized copies of the solutions manual to Blackboard so that you can even check that out even from home to check your work. And as always, if you run into any problems, just let me know. All right, thanks, and good luck on your quiz.